Okay. Hello and welcome everyone to week 5 problem solving session for NPTEL course Introduction to Operating System. And this week we are looking at scheduling algorithms. So we have quiz type questions related to scheduling algorithms, and I hope you had the time to go through the content for week 5 and you are already familiar. You have already learned about the scheduling algorithms. So here, let us look at these problems one by one. So the problem number 1 here is uh, that the average turnaround time with the shortest remaining time first and shortest job first scheduling for the 7 processes listed in the table is. So in this table you have 7 processes, P1 to P7. 80 is the arrival time, that is the time when this process came, and BT is the burst time, that is how much time the process will be spending on the CPU. How much time does it need to finish execution? So the question is asking you the average turnaround time with two different algorithms. First, the shortest remaining time first, and then the shortest job first scheduling. So can you guys tell me that what is a shortest job first scheduling and how is it different from a shortest remaining time first scheduling? Any answers? Okay, so shortest job first scheduling, in this the processor, so we are going to schedule the process which has the smallest execution time. Okay, and always the scheduling here in these type of questions, we are going to assume that we are going to start from timestamp 0, and we are going to look at the processes which are currently in the ready queue, that is which have arrived and by timestamp 0, and all among all of these processes we are going to then look at the process which has the shortest execution time or the shortest burst time, and we will schedule that process, and we keep doing that. Okay, so that is the shortest job first scheduling, that is we are going to schedule the process which has the shortest execution time. Now how is it different from the shortest remaining time first? The shortest in SRTF, what we do is that when we schedule the first process, say at timestamp 0, then whenever a new process arrives in the ready queue, we're going to check the execution time of the new process. If the new process has a shorter execution time, then we are going to schedule the new process on the processor and remove the current process. So at any point of time, we are always going to schedule the process which has the shorter remaining time, that is the shorter execution time. But in SJF, in shortest job first scheduling, once you have scheduled a process on the processor, then you will not remove it until it executes completely. While in SRTF, you remove the process if another shorter process arrives in the ready queue. Okay, that's the difference between these two algorithms. If it is not clear, then let me know. Otherwise, I would you can try this question and you can try to answer uh, what is the average turnaround time for these two scheduling. Is the question clear? Okay. Uh, so I'll just explain the solution. So let us first look at the shortest job first scheduling. So in the shortest job first scheduling, we are going to start from timestamp 0 here. So at time 0, only process 1 is available. That is, only process 1 is there in the ready queue. So we are going to schedule process 1. Now process 1 has burst time 8. So it is going to run for 8 time units. So from time 0 till end of 7th time frame, that is till the beginning of 8th timestamp, process 1 will be running. Okay, and after that, since now the current time now becomes 8, so all of these processes have arrival time less than 8. So all the processes would have come in the ready queue by then. Okay, so now all of these processes are available. Process 1 has already finished execution, and then among all the rest of the ready processes, we will find out the process which has the shortest execution time or the burst time. And among all of these, uh, process P6 has burst time of only unit 1. So we are going to schedule process 6 next. So here we schedule process 6. It is going to start executing at timestamp 8, and it will execute for 1 time unit. So it will finish before 9th time unit. Okay. After that, next, we are left with process P2, P3, P4, P5, and P7. Among these processes, P7 has the smallest timestamp. So we are going to schedule process 7 here. It will run for 2 time units, and after that, next the rest of the processes which are available, which have not finished, are P2, P3, P2, P3, P4, and P5. Among these, P4 has the smallest burst time of 3 units. So then we are going to schedule P4. Okay, and it will run for 3 units. Okay, from 11 till 11, 12, 13, and then it will finish before 14th timestamp. Then we are going to run P5 because it has burst time 4, which is less than 6 and 5. So we will schedule P5, and it will run for 4 units. After that, we'll schedule P3, which will run for 5 units. And lastly, we are going to schedule P2, which will run for 6 time minutes. So this will be the schedule of the processes. And if you have any doubts, then feel free to stop me and I will explain it again. But the question here asks you the average turnaround time. So what is the turnaround time? Turnaround time is the difference in time, is the difference in completion time and the arrival time. That is completion time, that is the time when the process finished execution completely, minus the time at which the process arrived in the ready queue for the first time. Okay, for example, process P1 here finished execution at timestamp 8, and it had arrived in the ready queue at timestamp 0. That is, you are going to read the arrival time from here. Okay, and you are going to find the completion time from this schedule. So according to this schedule, process P1 was scheduled here and it finished its execution at 8 timestamp. So turnaround time for process P1 here is 8 minus 0, which is 8. Similarly, turnaround time for process P2 here, process P2 here was scheduled in the end and it finished its execution at timestamp 29 and it arrived in the ready queue at timestamp 1. So turnaround time for process P2 is equal to 29 minus 1, which is 28. Similarly, for process P3, it finished executing at timestamp 23 and it arrived at 2. So 23 minus 2 is 21. For process P4, here it finished execution at 14 timestamp and it had arrived at timestamp 3. So 14 minus 3 is 11. And similarly for P5, P6, P7, we can calculate the turnaround times. Then the average turnaround time is the sum of the turnaround times of all the processes divided by the number of processes, and that gives us 13.4. So the average turnaround time when shortest job first scheduling algorithm is used is 13.4. Okay, and the question also asks you to report the average turnaround time when the scheduling algorithm is shortest remaining time first. So in that case, this will be the schedule, and let me explain it. So initially at timestamp 0, only one process has arrived, that is process P1. So we are going to schedule P1. Okay, and then it will run for 1 unit of time. After that, at timestamp 1, P2 also arrives in the ready queue. Now since P2 has arrived in the ready queue and it has a burst time of 6, while P1 at time unit 1 has remaining time as 7 units, and 6 is less than 7, that is why we remove P1, we preempt P1 and we schedule P2. Okay, so initially P1 was scheduled, it ran for 1 unit of time. After that, we preempt P1 and then we schedule P2. Okay, now P2 will be running and at timestamp 2, P3 arrives. So P3 arrives and its burst time is 5. Now by timestamp 2, P2 has run for 1 unit of time. That means remaining burst time now is 5 units. And 5 and 5, these both are equal values, and that is why we will continue executing P2. So the new process P3 which has arrived doesn't have a lower burst time, therefore we do not preempt P2. P2 continues to execute while P3 will wait in the ready queue. So P2 will continue to execute for second timestamp also. At timestamp 3, P4 arrives. Now P4 has burst time of 3 and now the remaining time of P2 is 4 units. Okay. At timestamp 3, P5 also arrives and it has burst time of 4. Now 3 processes are there. P2 is already running on CPU. It has burst time of 4, remaining burst time 4, while P4 arrived and has burst time 3. P5 arrived, has burst time 4. So among these processes, P4 has lower burst time and therefore we are going to schedule P4 and remove P2. So here we remove P2 and schedule P4, and P4 starts executing from timestamp 3, and after that at timestamp 4, P6 arrives. Now P6 process has burst time 1, which is smaller than the remaining time of P4. Now the remaining time of P4 is 2 units because it has already executed for 1 unit from 3 when it arrived till 4th time unit. So now remaining time for P4 is 2 units and the new process P6 has burst time of 1 unit. So we are going to schedule P6 here. Okay, now after that, since P6 has only 1 unit of time, burst time, so it will finish its execution before at the 5th timestamp. Now at 5th timestamp, P7 process arrives and it has a remaining time of 2 units. Now P4 also has remaining time of 2 units, and it was in the ready queue earlier than P7. So therefore, we are going to schedule P4 here after P6. We schedule P4 here after P6. Then P4 will execute for 2 units, and then it finishes its execution and terminates. After that, the next smallest process here is P7. So we are going to schedule P7 here. Then when it finishes, then the next smallest process, now 3 processes have finished, P4, P6 and P7. Now the left processes are P5 with burst time 4, P3 with burst time 5, P2 with burst time 4 because it has already run for 2 units, and P1 with burst time 7 because it has also run for 1 unit. So among all of these, since P2 had arrived first and it is there in the ready queue earlier, so we schedule here P2. So we are going to schedule here P2, and now when P2 finishes execution, then we are going to schedule P5, and then P5 will also finish its execution. After that, we are going to schedule here P3, which will run for 5 units, and then in the end, we are going to schedule P1, which is going to run for remaining 7 units. So this will be the schedule for shortest remaining time first scheduling algorithm. And now we are asked to calculate the turnaround time. So the turnaround time is the difference in completion time and arrival time. So turnaround time for process 1 is the completion time of process P1, which is 29, minus the arrival time of process P1, which is 0, so it is 29. Similarly, for process P2, the completion time of process P2 is 3. Sorry, here, yeah, here. The completion time of process P2 is 13, and the arrival time of process P2 is 1, so we get 12. Then turnaround time for process P3 here is completion time is 22 here from the schedule, and the arrival time is 2. So 22 minus 2 is 20. And similarly, we can calculate the turnaround times for process P4, P5, P6, P7. After that, we're asked average turnaround time. So we are going to add the turnaround times of all the processes and divide it by the number of processes, which is going to give us 12. That is the average turnaround time for these 7 processes for shortest remaining time first scheduling algorithm. So the problem was, this problem was given to us that there are these 7 processes listed in the table with their arrival time and the burst time, and we are asked that what is the average turnaround time with the shortest remaining time first and the shortest job first scheduling algorithm. And as we saw here, that when the scheduling algorithm is SRTF, then the average turnaround time is 12, and when it is SJF, then the average turnaround time is 13.4. So therefore, the answer here is 12 and 13.4. Is there any doubt? Okay. Okay, now let us look at the next problem. So the problem here is saying consider the context switching overhead of 1 unit. What is the context switching overhead while using SRTF and SJF scheduling for the 7 processes listed in the table? Include the context switching to load the first process. So what is context switch? So uh, whenever a process is scheduled on the processor, that is a context switch. That is, we are going to load the process state on the processor, and we are going to say load the register CR3 with the address of the process page table. And if the process was already running earlier and we had preempted it, then we are going to restore the context, that is the register values for that process. So here it is saying that whenever a context switch happens, then consider that the overhead is 1 unit, and now you have to tell what is the overhead, context switching overhead, when using SRTF and SJF scheduling for the 7 processes listed in the table, and also include the context switch to load the first process. So let us go back here to the schedule, and according to the schedule in SRTF algorithm, the first time we are going to load process P1, so that will be counted as context switch 1. Then we load process P2, that is context switch 2, then P4, context switch 3. So every time a new process is loaded, that is a context switch. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 context switches, and the cost of one context switch is given as 1 unit. So it is here the cost of context switching for SRTF is 10. Now for SJF, there are 1, 2, 3, 4, 5, 6, and 7. 7 context switches, and therefore the cost of context switching here is 7. And therefore your answer is option number 4, that is 10 and 7. Now the next problem, which is also based on this table, is for the processes listed in the table above, the schedule length is dash with the FCFS scheduling scheme. So what is a FCFS scheduling? FCFS stands for first come, first serve. So the process whose arrival time is shortest will be served first. So whenever the process are served in the order that they arrive in the ready queue. So for example, here first process P1 comes, so it will be scheduled and it will be allowed to run until it finishes its execution, that is for 8 time units. Then by that time these processes would have come in the queue, but these processes uh, would be there in the queue in the order of their arrival time. Okay, so P2, then P3, then P4, P5, P6, and P7, and we're going to schedule the processes on the processor in the order of their arrival time. So then we are going to schedule process P2, which will run for 6 time units, then P3, which runs for 5 time units, then P4, which runs for 3 time units, and then P5, which runs for 4 time units, P6 runs for 1 time unit, and P7 runs for 2 time units. So that will be the schedule for first come, first come, first serve scheduling scheme, and it is asking you the schedule length. That is, when the first process was scheduled on the processor till the last process finished its execution, what is the total time that is being asked here, and that is the sum of all the burst times. That is the sum of the burst time of all the processes, and that is equal to 29. So the answer for this question here is 29. Now let us look at the next question, which is consider 3 processes that start simultaneously. Each process from start to finish takes 40, 50, and 60 milliseconds respectively. Of this, the first 20% of the time is spent waiting for IO events and the next 80% time for computation. The scheduler uses first come first served scheduling, assuming that all IO operations are overlapped. How much time in milliseconds is the CPU idle? And your options are 8 milliseconds, 16 milliseconds, 18 milliseconds, 40 milliseconds. So here the processes are starting simultaneously. That is, we can assume that the arrival time is 0. They all arrive at the same time. And then um, first process takes 40 millisecond to finish. Second is taking 50 millisecond. Third is taking 60 milliseconds. But the question says that the first 20% of the time is spent waiting for IO. So they will be in waiting state for 20% of the time which is given here, and rest of the 80% they are going to the next 80% is they are going to perform computation. Okay, and it says that assuming that the scheduling used is FCFS and all of the processes have their IO events in the beginning, that is in the beginning of the uh, process, and all the IO operations are overlapped, then how much time in milliseconds is the CPU idle? That is when there was no process, when no process was ready to be scheduled on the CPU. So now for this question, it says that 20% of the time is in waiting state for every process. So 20% of 40 milliseconds for first process is 8 milliseconds. Then 20% of 50 milliseconds is 10 milliseconds, and 20% of 60 milliseconds is 12 milliseconds. So the first process is going to be um, waiting for IO to finish from timestamp 0 till timestamp 8. Second process will be waiting for IO from 0 to 10 milliseconds, and the third process is going to be waiting for timestamp to become 0 from 0 to 12 milliseconds. Okay, and after that, uh, so after the on the 8th millisecond, the first process will be put in the ready queue, and then it will be scheduled on the processor. Okay, and after that the time will be for 32 time units. For the rest of the time, that is 80% of the time, it is going to be executed. And since 80% of the time of 40% is 32 milliseconds, it's going to be executed for next 32 milliseconds. By that time, process 2 and process 3 would have arrived. So the processor here is idle only in the beginning, 8 milliseconds, and rest of the time the processes are available to be scheduled. So therefore the answer to this question here is 8 milliseconds. Okay, then let us look at the next problem, which is a continuation of this question, and it says that from the data given above, which of the following is the average turnaround time considering only the time when a process is either running or in the ready state? So you have to consider here, uh, do not consider here the time when the CPU was idle, that is the first 8 milliseconds. If you remove that, then for the rest of the schedule, uh, what is the average turnaround time? when the processes are either in ready queue or they are running. Okay, so 20% of the times the processes are waiting, and rest of the time they are uh, that is their computation time. Okay, so the remaining time for process 1 when it will do computation is 32 milliseconds. For second process, the burst time or computation time is 40 milliseconds, and for the third process the remaining time is 48 milliseconds. Okay, so these are the burst time or the execution times of these processes. They're not the execution time. The execution time is the whole time, which is 40 milliseconds, but the time for which the processes need computation, that is to they need to run on the processor, and that is 32 milliseconds, 40 milliseconds, and 48 milliseconds for process P1, P2, and P3 respectively. Now the turnaround time we have to compute. So the first process, it will start executing at 8th millisecond, and then it will execute for 32 milliseconds because that is the time it will be it needs to execute. And so uh, by that time, 8 plus 32 will be 40. So that means here the turnaround time, the completion time for process 1 is 40, and the time when it arrived in the ready queue, when it was available for to be scheduled, was 8. So 40 minus 8 is 32. After the first process finishes its execution, next process will be scheduled on the processor, and it will run for 40 milliseconds. So it is scheduled after the first process finishes, and the first process is finishing at 40 milliseconds. So 40 plus 40 will be the completion time of process 2. So the completion time for process 2 is 80, and arrival time, that is the time when it arrived in the ready queue, is 10. So 80 minus 10 is 70. So note that here the arrival time is the time when it arrived in the ready queue and not the time when it had arrived initially. Okay, so then the process P3 is scheduled after process P2 finishes its execution. It finishes execution at timestamp 80. So after that, P3 is scheduled. It runs for 48 milliseconds. So it finishes its execution at time 128. So 128 minus the ready time when it became ready, when it arrived in ready queue, which is 12, is 116. Now, these are the turnaround time of the individual processes. To find out the average turnaround time, we just add them and divide by 3. That gives us 72.6. So here the answer to this problem is 72 milliseconds. Okay. Now, this is all the problem 6 is also continuation of this problem, and it is asking that for the data given above, the schedule length is dash assuming shortest remaining time first scheduling algorithm. So here the schedule length when scheduling algorithm is SRTF. So then so first of all, process P1 is scheduled at timestamp 8. and its remaining time is 32 milliseconds. Okay, so this will start executing, and the remaining time of the next process is 40 milliseconds, and for process 3 is 48 milliseconds. So they will be scheduled in this order only. First, process P1 will be scheduled. When it finishes execution, the process P2 is going to be scheduled, and then process P3 will be scheduled. Okay, so they will be scheduled in this order, and the schedule length here is asked. So the process is finishes executing at timestamp 128, and the first process was scheduled at timestamp 8. So that is why the length of the schedule here is 128 minus 8, that is 120 milliseconds. So the schedule length here is only 128 milliseconds. So the next question here is the shortest remaining time first algorithm is not practical. First, its time complexity is huge, which makes it unsuitable for real systems. And the second statement says that it requires knowledge of the burst time, which can be easily predicted. So you have to tell which of these statements is true and false. So here the statement one, it is saying that SRTF complexity is huge and it makes it unsuitable for real systems. This statement is false because whenever a new process arrives, we can we can always keep the ready queue in a sorted manner. We can all Whenever a process arrives, we can put it at the location according to the ensuring that all the processes in the ready queue are sorted according to their burst times, remaining burst time. Okay, so then the time complexity is not huge because we are always going to pick the first process from the ready queue and going to schedule it. And second one says that it requires knowledge of the burst time, which is true. So we need to know that what is the remaining burst time of the process, but it says that it can be easily predicted, which is not true. So it is not easy to predict that how long the process is going to run. So this statement is also false. So both the statements are false here, and the answer is false and false. So here the next question is, consider three processes P1, P2, P3 with arrival times 013 and burst time 654 unit respectively. What is the order of completion in SJF RR scheduling with time size of 2 units? So first, what is the order of completion in shortest job first scheduling? Okay, so here the first process arrived at timestamp 0, so we will schedule it, and it has burst time 6, so it will run for 6 time units. Okay, because it is not preemptive, we are not preempting any processes in SJF, so it will run till 6 units. By that time, process P2 and P3 would have arrived because the arrival times are 1 and 3, and then among process P2 and P3, the smaller process is P3. It has burst time of 4 while process P2 has burst time 5. So we are going to then schedule process P3, and then it will finishes its execution. After that, we are going to schedule process P2. So first process P1 is scheduled, then process P3 is scheduled, and then process P2 is scheduled. So answer here is P1, P3, P2. Option number 4. Next here we have, consider three processes P1, P2 and P3 with arrival times 013 and burst time 654 respectively. The same question, and now you have to answer here the order of completion in round robin scheduling. So for this question, it's a little bit tricky, and so first of all, in the ready queue, so I'll just write it here. Initially, the ready queue will be empty. Let us keep the answer here, and so this is the answer, but now we are going to solve it here. Okay, initially the ready queue is empty. So at timestamp 0, process P1 arrives. We put it in the ready queue first, okay, and then we are going to schedule it. So when we schedule a process, like we removed it from here and we scheduled it here. Okay. Now it runs for two time units. Okay, because it says that the quantum here is 2 units, so it will run from 0 till 2. Okay. At timestamp 2, now what happens before timestamp 2? What is happening that at timestamp 1, process P2 has arrived and it is there in the ready queue. Now process P2 is already in the ready queue, and after that at timestamp 2 we are going to preempt process P1 and we are going to put it in the ready queue, and we are going to pick the process P2 from the ready queue. So we will pick it, that is we are going to remove it from here and we are going to put it here. Now this will run for two time units, okay, that is from 2 to 4. And its burst time is, P1's burst time is 6 units. For it is 5. Okay, so it will run for 2 time units now. After that, since at timestamp 3, process P3 would have arrived. So here process P3 will be there in the ready queue. So when P2 is preempted, then the top of the ready queue has P1. So P1 will be scheduled here again, and it will run from 4 to 6. And also before that, actually, we're going to remove P2 here from the processor. We are going to put it in the ready queue. After that, we are going to remove P1 from here, put the P1 in the schedule. It will run from 4 to 6. Now, P1, when it 2 time minutes are finished, it will be put in the ready queue, and P3 will be removed and P3 will be put here for execution from 6 till 8. Now so far P1 has run for 4 time minutes, P2 has run for 2 time minutes, and P3 has run for 2 time minutes. So remaining time for P1 is 2 units, for P2 3 units, and for P3 2 units. Okay, now P3 when it finishes execution will be put in the queue again, and then we will remove P2 and we will run P2 for 2 units from 8 till 10. Now when P2 finishes execution, now P2 has run for 4 units, but its burst time is 5. So we again, it is still not finished. So we will put it again in the queue. Then we are going to remove P1 from the queue and we are going to schedule it. We'll run it for 2 time minutes from 10 to 12. Now P1 has run here initially for 2 units, then again 2 units, and now 2 units. So P1 finishes its execution now because it has run for 6 units. Okay, so the process which is finishing first here is P1. Then and therefore we are not going to put it in the ready queue now because it has finished execution. Now from the beginning of the ready queue, we have P3. So we're going to remove P3. We're going to schedule it here. P3 will run from, now how long will P3 run? P3 has run for 2 units. Its burst time is 4. So it will run for 2 more units here. Then after that, P3 will also finish, and we are not going to put it in the ready queue. Now P2 will is there in the ready queue. We'll remove it, and then we are going to schedule it here. Now P2 has run for 2 units here, 2 units here, and only 1 unit is left. So it will run for 1 unit here. And then P2 is also, so we had to first remove it from here, then put it here. Now all the processes have finished execution, and the first process to complete was P1, then P3, and then P2. So answer here is option number 3 again, which is P1, P3, and P2. Okay. So this is the problem number 9. Now let us look at the next problem, which says that Professor X suggests a method to alleviate starvation in scheduling algorithms. Under this new scheme, processes get a priority number. The priority of the process is considered by the scheduling algorithm when scheduling. The new scheme will alleviate starvation. Is it true or false? So the question here is saying that every process is assigned a priority, and then we are going to schedule the process based on the priority. Say a process with higher priority will be scheduled first. Does this scheme alleviate starvation or not? So the answer here is false. This does not alleviate starvation, and the reason is because it is possible that, um, say, the process Y is waiting in the ready queue, and every time a new process arrives with a higher priority. So it is possible that it can wait forever, and all the processes which arrive in the ready queue have a priority higher than process Y, and therefore it will be starved. So the answer here is false. Now next question is, starvation can occur in shortest remaining time first algorithm and shortest job first algorithm. True or false? So the answer here is also true. So answer here is true because every time it is possible that your process Y has burst time 100, and every new process which is arriving in the ready queue has a burst time smaller than 100. So your process Y will keep waiting while the new processes will keep finishing, and new processes will keep arriving, and they will be getting the CPU. So your process Y will never get a chance to execute, and its burst time will not be reduced, and it will be there in the queue waiting forever. So starvation is possible in for both SRTF and SJF. So the answer here is true. Now next question is, there are 4 processes A, B, C, D. They have estimated time of completion of 5, 7, 9, 11 nanoseconds. They are scheduled in round robin fashion, and the time slice is of 2 nanoseconds. The processes A, B, C, D arrive at 0, 1, 2, 3 nanoseconds respectively. At what time will the processes complete execution? So the answer here is uh, So the answer is quite simple. The process P1A, process A arrives at time, process A arrives at time 0. It will be given CPU for 2 nanoseconds, for 2 units. So it will execute from 0 at 0 and 1. And it will yield the CPU at time unit 2. at timestamp 2. So by timestamp 2, process P1 and P2 has arrived. Okay, then process P1 will be given the CPU. It will run for 2 units. That will be for till the end of till the beginning of fourth timestamp, and by that process D also has arrived. So all the processes now have arrived. Okay, and every process is now going to run for 2 seconds in a round robin fashion. So overall, no time is being wasted here. Okay, all the processes are getting 2 nanoseconds of time for this of the CPU, and they are going to be executed one after the other in the round robin fashion. So therefore, the total time the processes take to finish execution is nothing but the times, sum of the burst time of the processes here, which is 5 plus 7 plus 9 plus 11, and that is equal to 32. So the answer here is 32 nanoseconds. Now the next question is, many more context switches occur when using non-preemptive shortest job first scheduling instead of round robin scheduling. True or false? So the answer here is false, because in round robin scheduling, a process is preempted whenever the time slice finishes. While in shortest job first scheduling, a process is not preempted until it finishes its burst time. So there are less number of context switches in shortest job first scheduling than round robin scheduling. So the answer here is false. The next question is, a round robin scheduling algorithm with a large time slice will behave similar to a first come first serve algorithm. This is true because uh, if the time slice in a round robin scheduling is very large, say it is infinite, like, then that is equivalent to the first come first scheduling. Whenever a process arrives, it will be given the CPU, it will run until the end of its burst time, then it will release the CPU, and then the next process which is present in the ready queue will be given the CPU, and again it will run until it finishes its execution. So if the round robin scheduling algorithm time slice is bigger than it is larger than the time slice, that time slice is larger than the burst time of all the processes, then the round robin scheduling will behave similar to a first come first serve algorithm. So it is true. The next question is, the overhead due to context switches is less if the time slice durations are small. True or false? So the answer here is false, because if the time slice is say 1 unit, then the processes will be preempted at every one time unit. Okay, so if there are only two processes and their burst time is say 2 units, then, and if the time slice is 1, then process P1 will run for 1 unit, then process P2 will run for 1 unit, then process P1 will run for 1 unit, then process P2 will run for 1 unit. So there are 4 context switches here. Instead, if the time slice is made 2 units, then first process P1 will be scheduled. It will run for 2 units, finish its execution. Then process P2 is scheduled. It will run for 2 units and it will finish its execution. So only 2 context switches. So the overhead due to context switches is actually more if the time slice durations are small. So hence this statement is false. So this was the last question for today's quiz, from today's quiz. Thank you so much for your time, and with this I will end the session now.